Hi everyone, I welcome you to yet this another episode of Uncertainties. Actually, this is a continuation of part one, where we were dealing with the solved past paper questions under errors and uncertainties. And today I want us to finish up this. Remember, this is AS Physics. AS Physics. This is AS Physics. This is 9702. I said these questions are going to be picked from AS papers, paper 1 and paper 2. My name is IBM and I welcome you to this episode of concluding with the uncertainties by handling or making ourselves comfortable with worked examples. So in part 1 we stopped on question 19. I think it had a problem because of the device failure. So I had to start with question 19 again. So let's go back to question 19. Okay, so question 19 was telling us that they gave us the mass, they gave us the length, original length, diameter, extension, and they gave us the expression for Young's modulus. And they asked us they told us that the calculated value of E is actually 1.6 times 10 power 10 newtons per meter squared. How should the calculated value of E and its uncertainty be expressed? So the calculated value is there, we don't need to calculate it again. All we need is to find the uncertainty. So since the answers are expressed to absolute values, absolute uncertainties, we shall need to find the absolute uncertainty in E. So let's start. So the absolute uncertainty, sorry. So the absolute uncertainty in E, because they have given us mass, the absolute uncertainty in E will be equal to, because we say that the constants 4 and pi do not affect the uncertainties, so this will be the absolute in M divided by M plus the absolute in L divided by L, because G is given as a constant here with no uncertainty, we shall not include it in the uncertainty. Then plus D has a square, so this will be twice absolute uncertainty in D over D plus absolute uncertainty in E over E. We shall multiply this by the true value of E. Okay, so if we substitute, this will be M, that is 0.002 divided by 2.300 plus for L, this is 0.005 divided by 2.864 plus for D, this will be 2 times 0.01 divided by 0.82. Then for E, this is 0.2 divided by 7.6. Now I will multiply this with the true value of E, which is actually 1.61 times 10 power 10 times 10 power 10. Now I want you to note that I've not bothered in converting the units, because you notice I'm dividing quantities with the same units. The absolute uncertainties have the same units as the most likely value, so I don't need to convert units. Okay, so let's try to press our calculator and see what we get. You can press yours too and see what you get. As a physics student, you learn to use brackets. This will make you confident with, or get used to your calculator, so that it is always easy to press it when you want a value. So I'm pressing mine, open brackets, 0.002 divided by 2.3 plus, open another bracket, 0.005 divided by 2.864, close that bracket, plus, open bracket, 2 times 0.01 divide by 0.82, close that bracket, open yet another one, 0.2, divide by 7.6, close that bracket. So the sum is 0.05332. I multiply this by 1.61, exponent 10. And this gives me, I hope it gives you almost the same thing. This is giving me 474, not point, 679.3. I want to write it in standard. I want to express it as a power of 10. So this is the same as 8.58 times 10 power 3678. So this is times 10 power 8 times 10 power 8. Okay, so since it is times 10 power 8, but then I said when we were learning uncertainties, we only manipulate the power of 10 for the absolute uncertainty. This is the absolute uncertainty in E. Absolute uncertainty in E. We manipulate the power of 10 so that it looks like the power of, it looks like that of the true value, which is power 10. So you will notice that this to power 10, I will move 2 steps in front. So this will be 0.05, sorry, not 5, 0.0858 times 10 power 10. I've now moved 2 steps to the left, so it becomes positive power 10. To one significant figure, this will be 0.09 times 10 power 10. Now these are 2 decimal places, therefore it makes sense that we shall write our true value as 1.61 times, plus or minus 0.09 times 10 power 10. So it means we shall write our value of E as 1.61 plus or minus 0.09 into brackets times 10 power 10. So this D would be the correct value. It would be the correct alternative for that, for question 19. So I hope this is very clear. Now this is quite hard for students to comprehend. You just look at the uncertainty, it is raised to power 8, but we cannot manipulate the power of 10 for the true value. We just ensure that the power of 10 for the absolute uncertainty is the same as the power of 10 for the true value. So this was 10 power 10. I also ensure that the absolute uncertainty is 10 power 10. So how do I do this? Notice that I moved 2 steps to the left for a positive power. For a negative power, that will be 2 steps, that will be to the right. And I hope that is clear. Let's move to the next one, question 20. The current in a block of a semiconductor is 30.0 milliamperes when there is a potential difference of 10.0 volts across it. The dimensions of the block and the direction of the current in it are shown. We can see the current, the dimensions, maybe one can be length, width, and so on and so forth. The electrical meters used are accurate too. So the meters have uncertainty plus or minus 0.1 and 0.1 volts. So this is for the ammeter, the other one is for the voltmeter. The dimensions of the block are accurate too. So these values have these uncertainties. What is the resistivity of the semiconductor? So from resistance, we know that resistance is equal to rho L over cross-sectional area. Resistance is rho L over cross-sectional area. L will be the length of the conductor. L will be the length of the conductor. Now the question will be, what shall we take as the length of the conductor? And then rho is the resistivity, R is the resistance, and A is the cross-sectional area. So to begin with, they have given us the current in a block of a semiconductor when there is a potential difference V across it. So this is going to be our cross-sectional area. The dimensions of the block are that. So our cross-sectional area is going to be equal to 15 times 10 power 15 times 10 power negative 3 times 30 times 10 power negative 3. This is going to give you the cross-sectional area, but I will not do that for now. Let me first manipulate this. Now the length, what length of the wire? We shall take the length of the wire in the conductor. You notice that the wire is entering from the other side and coming out from this side. So the section of the wire which is in the cube is actually equivalent to this length here. So our value of L is actually going to be 15.0, maybe times 10 power negative 3 if you want it in meters. This would be in meters squared. And what else? What else? Resistance. Of course, resistance can also be found as potential difference across or divided by current. Resistance can be found as potential difference divided by current. So before I substitute anything, let me just manipulate all this. I make row the subject. So now I have that we have that resistivity is going to be equal to resistance times cross-sectional area over length, which will actually be equal to V times cross-sectional area over I times L. That will be our expression here for resistivity. Let me substitute directly. Remember, A or cross-sectional area will be actually this length and that height there. So I'm simply substituting. So resistivity is going to be equal to V. V is 10.0 times cross-sectional area, which will be 15 times 10 power negative 3 times 30 times 10 power negative 3 divided by current I, which is 0. I is 30 times 10 power negative 3 because it is given as milliamperes, then times the length of the conduct, the section of the line of the wire in the cube, which will be equal to this length here, because when the current is entering from the other side, it is like the length of the wire in the cube is the same as this length here. So this will be 15 times 10 power negative 3 to change it to meters. So we can press our calculator very fast. We can check our calculator. So this is 10 times 15 exponent negative 3 times 30 exponent negative 3 divided by 30 exponent negative 3 times 15. Oh, I'm even wasting my time. You can see that this one is the same as this, that one is the same as that, so the resistivity is 10. We needn't even check that. So resistivity is actually 10.0 ohm meters. So what remains is for us to check the resistance, the word uncertainty. So we shall say that because resistivity is equal to VA over I times L. This is, there is multiplication, there is division, so we just add the fraction uncertainties. So the absolute uncertainty in rho is going to be the absolute in V over V plus the absolute in A over A plus the absolute in I over I plus the absolute in L over L. Now for A, they have not given us the what? The base units, I mean the uncertainty for A. But we know that uncertain A is one length. Let me call this maybe I will call this breadth, and I call this one height. So it will be the breadth times the height. So it means each of these has uncertainty plus or minus 0.2. Therefore, remember I'm going to multiply this by the true value of resistivity, which is 10. Now I'm substituting. So to substitute, I now have that the absolute is equal to, for V is 0.1 volt divided by 10, 0.1 divided by 10 plus. For A, I have breadth and height. So for in each it is 0.2, so I will say 0.2 divided by 15.0 plus, this is maybe the breadth, and the height I have also 0.2 divided by, the height is 30.0. I will not change the units because they're in millimeters. Then plus, for I, the uncertainty is 0.1 in milliamperes divided by 30.0 in milliamperes plus, for L it is also having the uncertainty as 0.2. So this is 0.2 millimeters divided by 15.0. Then I will multiply all this by the true value of the resistivity, which is 10.0. So let me check. You can also now pick your calculator and check. Open the brackets, 0.1 over 10 plus, open another bracket, 0.2 over 15 plus, open another bracket, 0.2 over 30, close that bracket, plus, open another bracket, 0.1 over 30, close that bracket, plus, open another one, 0.2 over 15, close that bracket. So when I press the calculator, that simplifies to 0.046666. When I multiply it by 10, it becomes 0.4667. So I'll get this as the absolute in rho is actually 0.467. To one significant figure, it is approximately 0.5. Therefore, my correct answer will actually be C. C will be my correct answer. I hope that was tiring, but it is easy. Next, the double slit interference experiment is used to determine the wavelength of light from a monochromatic source. The following are measurements: slit separation, A is given, X is given, D is given. What is the percentage uncertainty and the calculated value, the calculated wavelength? So for double slit, Young's double slit, we know that lambda is equal to AX divided by D. Lambda is AX over D. What is the percentage uncertainty in lambda? Because of multiplication and division, we shall deal with fractional. Multiply both sides by 100, it becomes percentage. So fractional in wavelength is equal to fractional in A plus fractional in X plus fractional in D. Then I'll multiply both sides by 100. This side by 100 is percentage. Even this side by 100 is percentage. So I will say that the percentage uncertainty in wavelength is equal to, for A, that is 0.02 divided by 0.50 plus, for X, that is 0.1 divided by 1.7 plus, for D, 0.002 divided by 2.000. So I will simply multiply this by 100. There is no need for me to multiply with the wavelength this side. It doesn't make any sense. I've already said an absolute uncertainty in wavelength over wavelength times 100 is already wavelength it is already percentage uncertainty in wavelength. So I don't again multiply by the true wavelength the other side. That's why you have not even found it here. I didn't bother to calculate it. So when you press the calculator, So open the first bracket, 0.02 over 0.5, close the bracket, plus open another one, 0.1 over 1.7, close that bracket, plus open another one, 0.002 over 2.000, close that bracket, times 100. So this is giving 9.98. So this is 9.98, 9.98%, which is approximately 10%. So this makes D as our answer. I hope that is fine. Let's continue. Question number 22. A quantity y is to be calculated from this expression. The percentage uncertainties in P, X, and Q are shown. What is the percentage uncertainty in y? So because of multiplication, because of division, because of a square, we add either the percentage or fraction uncertainties. So fraction uncertainty in y will be given like that. When I multiply it by 100, its percentage in y will be equal to the fraction in p over p times 100 plus the fraction in x times 100 plus twice, because of the square on q, the fraction in q over q times 100. So that means percentage in y is simply equal to percentage in p plus percentage in x plus twice percentage in q. This will be 6% plus 2% plus 2 times 4%. And this gives us 8 plus 8, which is 16%. I think this is the easiest. Okay, let's continue to the next part of the question. The next question, rather. Question number 23. One end of a wire is connected to a fixed point. A load is attached to the other end so that the wire hangs vertically. D is the diameter. The diameter of D of the wire and the load F are measured as that. So load D is that and load is that. The stress sigma in the wire is calculated by using the expression that show that the value of sigma is that. So here I just substitute. So I'm just simply substituting sigma. So the sigma equals to 4 times F, 25.0 divided by pi. Then D is given as 0.4 but is in millimeters. So times 10 power negative 3, and this is squared. I press my calculator. You can press yours. 4 times 25 divide by open brackets, or divide by open brackets. Okay, you can first divide by pi into brackets, 0.4 exponent negative 3, close the bracket, and square. So when I simplify this, it is giving me actually 1.989 times 10 power. This is 368 times 10 power 8 newtons per meter squared. So this is approximately 1.99 times 10 power 8 newtons per meter squared as required. Determine the percentage uncertainty in sigma. This is very easy now. So percentage uncertainty in sigma will simply be percentage uncertainty in sigma is going to be percentage uncertainty in F plus twice percentage uncertainty in D. The constants 4 over pi will not affect the percentage of fraction uncertainties. So we now substitute. So this will be for F. I will get the absolute 0.02 divided by the true value, which is 0.40 times 100. That is percentage in F plus twice times for D. Sorry. sorry. I've used, okay, this is F, this is D. I'll just multiply this by 2 so that is D. Then for F, let me erase this. So D is this one times 2. Then for F to be 0.5 divided by 25.0, then multiply this by 100. Let's check. We press the calculator. 2 times 0.02 divided by 0.4, that is times 100. So this is 10. This is 10% plus 0.5 divided by 25 times 100. This is 2%. So the total is actually 12%. So the percentage uncertainty in sigma, without wasting time, is actually 12%. Okay, maybe the question is still continuing. Let's check. Oh, it's another question. The speed v of a transverse wave is given by that. On a uniform string, T is the tension, therefore it is a force in newtons. An experiment is performed to determine the speed. The measurements are shown in the table. Use the data to calculate the speed. So let's straight away find the speed. Note that this is in centimeters, this is in grams. You must ensure that they are in SI units. So the speed is going to be equal to the square root of T is in SI units, 1.8 in newtons. L is in centimeters, so I will change it to meters. Divide by 100 becomes times 1.26. Divide by mass is in grams, so it will be 5.1 times 10 power negative 3. When you press your calculator, let's check. So pressing the calculator, 1.8 times 1.26 divide by open brackets 5.1 exponent negative 3, then square root. So this is giving me 0.088 meters per second. Okay, let's see the next part of the question. Perhaps it is talking about the uncertainty. Determine the absolute uncertainty in V and state V with its absolute uncertainty. So we have that V is equal to the square root of TL over M. And we have already got our value of V as 21.088 meters per second. So we shall briefly go to the previous page, because anyway, before we look at that, since they have given us percentages in these values, so the percentage uncertainty in V will be equal to, because of the power, the root, which is power half, we said we multiply the power by the percentages or the fraction uncertainties. So this will be a half into the percentage in T plus the percentage in L plus the percentage in M. So all we need is to sum up the percentage uncertainties. I have to go back to the previous page. Is it this page? Sorry. I have to go back to the previous page where I can find the uncertainties. Okay, for T, it is 5%. For L, it is 1%. And for M, it is 2%. Okay, so we can substitute. Can now go and substitute. So this will be for T, which is 5%, plus for L, which is 1%, plus for M, which is 2%. So this is 5, 6, 7, 8 divided by 2. That becomes 4%. But that is percentage, remember? Therefore, the absolute uncertainty in V will be given by 4 over 100 times the true value of V, which is 21.088. Let's press the calculator very fast. Answer times 4 divided by 100. So this is giving us 0.84. 0.84. But this one significant figure to be 0.8, and that is one decimal place. That means we shall write our answer also to one decimal place. So our true value of V becomes 21 point. We round off this one decimal place, it becomes 0.1 plus or minus 0.8 as our correct answer. I hope that is also easy. Let's move to the next question. Question number 25. A metal wire of length L has a circular cross-sectional cross-section of diameter D. The volume or L of the wire is given by that expression. The diameter has been given, the length and the uncertainties plus the mass. Calculate the density of the metal Y with its absolute uncertainty. Give your answer to an appropriate number of significant figures. So to begin with, we know that density is mass over volume. The volume has been given, so this is mass divided by volume, which is pi d squared L over 4. The 4 goes up, it becomes 4m divided by pi d squared L. You see, I told you last time we avoid first of all calculating the volume. It again makes calculating uncertainties hard. But when I have an expression like this one, it becomes easier to calculate the uncertainty. So let's substitute. Density is going to be equal to 4 times the mass. The mass has been given as 0.0, sorry, it's not 0.0. Sorry. I have to check for a tool here. So the mass has been given. The mass has been given as 0.225. It is in grams, so I'll say times 10 power negative 3. I divide this by pi divided by pi. D has been given in millimeters, so I will say 0.38, but times 10 power negative 3, this is squared. Then times L, which is 25 centimeters, so it is 25 times 10 power negative 2. How to press the calculator very fast? You can also press yours. 4 times 0.225 exponent negative 3 divided by pi times 25 exponent negative 2 and times 0.38 exponent negative 3, and this is squared. So my answer is, I'm getting 700. I'm getting density to be 7935.7 in SI units, kilogram per meters cubed. You can even see this question was 5 marks. That means it involves a lot of work. So resilience is very important. So let's find the absolute uncertainty now. Since we already have a simplified formula, density is equal to 4m over pi d squared L. Then we shall simply say that the absolute uncertainty in a row will be equal to, we ignore the constants, the absolute in m plus absolute in m over m, that is the fraction, twice absolute in d over d plus absolute in L over L. I'll multiply this by the true value of D. By simple substitution, in M I have 0.001 divided by 0.225 plus 2 times 0.01 divided by 0.38 plus in L 0.1 divided by 25.0. Then I multiply this by density, which we have got there, 7935.7. Okay, we can press our calculator, open brackets, 0.001 divided by 0.225 plus, open another one, 0.02 divided by 0.38 plus, open another one, 0.1 divided by 25. Then I multiply by the true value, 7935.7. So this is giving me 484.7. So this is giving me the absolute uncertainty as 484.7. But remember, the teacher said the absolute uncertainty is good enough to one significant figure. So we must record this to one significant figure. This will be approximately 500, one significant figure. It is ending in two zeros, and the teacher said we go back and rewrite the true value as a whole number ending in two zeros. So because this is 500, the value here should also end in two zeros. So I'll go back and modify this. Therefore, it becomes 7900. That is the most appropriate way of writing the true value with its absolute uncertainty. I hope that is home and dry and understandable. Next, the student determines the density of steel by taking measurements from a steel wire. The mass is given, the length is given, the diameter is given. He uses the equation density is equal to that. This is almost similar to what we have just done, but we shall do it very fast. What is the percentage uncertainty in his calculated value of density? So we shall simply say percentage uncertainty in density is equal to percentage uncertainty in mass. We ignore the 4 plus twice percentage uncertainty in D because D is squared plus percentage uncertainty in L. So this will be for mass 0.1 divided by 6.2 times 100. It is percentage in mass. Plus for D, this will be 0.01 divided by 2.00 times 100%. That is percentage in D. Then for L, it will be 0.1 divided by 25 times, of course, 100. That is percentage for L. So when you add up this, let's just press the calculator. 0.1 divided by 6.2 times 100. My calculator is jamming. 0.1 over 6.2 times 100. So this is 1.6 plus 0.02 divided by 2 times 100. Oh, this is 1%. So this is 1% plus 0.1 divided by 25 times 100. This is 0.4%. So when you sum up, I think you get 3.0. So this is giving us 3.0%. So the answer is D. Next, The mass m of a metal sphere is given by that expression. Calculate the diameter d. Calculate the diameter d. So we make diameter the subject in this equation. So making the diameter, so diameter will be equal to 6m divided by pi times rho under cube root. Then we substitute. This will be the cube root of 6 times the mass 7.5 divided by pi times the density, which is 8100. So I know most of you, instead of finding the cube root, you'll find the square root. So this is 6 times 7.5 divided by, open brackets, pi times 8100. Then we find the cube root. Cube root, shift cube root of the answer. So this is giving us 0.120. I suppose the next question is going to tell us to find uncertainty in D. So the percentage in density is 5% and the percentage in mass is 4%. So we are most likely going to find the absolute answer or percentage uncertainty in D. So let's see the next page. Use your answer in Roman 1 and the data in the figure to determine the value of D with its absolute uncertainty to an appropriate number of significant figures. So since they have given us the formula, or we have found out that D is actually the cube root of 6m over pi times rho. And they have given us the percentage uncertainty, so we shall just straight away find the percentage uncertainty in D. So percentage in D, because of the cube root, it is power third. So we multiply the power by the percentage uncertainties. We ignore 6 and pi. So this will be a third into percentage uncertainty in m plus percentage uncertainty in rho. And when you substitute, it becomes a third into m is 4%, plus rho, which is 5%. So the percentage in D is actually 9 divided by 3, which is 3%. That is percentage uncertainty in D. We want absolute. So the absolute uncertainty in D is going to be equal to 3 divided by 100 times the true value of D. The true value of D, it is still on my calculator, it is 0.1, 0.12, 0.1209. So that times 3 divided by 100. So this is giving us 0.0036. To one significant figure, it is 0.004. So these are 3 decimal places. So I will go back and write my answer to 3 decimal places. So my correct value of D will be 0.121. Note that was 09. Then plus or minus 0.004. So that will be the correct value of D with its absolute uncertainty. Next. In a simple electrical circuit, the current in a resistor is measured as that. The current is measured as this with the uncertainty. The resistor is marked as having a value of that. If these values were used to calculate the power dissipated in the resistor, what would be the percentage uncertainty in the value obtained? So simply power is equal, we have I and R, so power is I squared times R. There is a power, there is multiplication, so we just add the percentage uncertainties. So the percentage uncertainty in power will be equal to, because of the power, the square, this will be twice, percentage in I plus percentage in R. We just add. So this will be 2 times Percentage in I, absolute 0.05 divided by 2.5. Of course, this is times 100. To change it to percentage, plus for the resistance, this one has been given as percentage, so I'll just say plus 2%. So we simplify, press the calculator. 2 times 0.05 divided by 2.5 times 100, that is 4%. So this is 4% plus 2%, which gives us 6%. So the percentage uncertainty in the power dissipated in the resistor would be 6%. Next, the beam is clamped at one end and an object X is attached to the other end of the beam as shown. The object is measured to oscillate vertically. The time period T of the oscillation is given by that. So they have given us the time period as period T is equal to K square root of M L cubed over E. M is mass of X, L is length, and E is the Young modulus. E is the Young modulus and K is a constant. Okay, I think the question continues. Let's see on the next page. Data in SI units for the oscillations of X are shown. Calculate E and its actual uncertainty. So they have given us that T is actually equal to the square root of M L cubed divided by the Young modulus. They want us to calculate E. I'm making E the subject straight away. Square both sides, it becomes T squared is equal to M L cubed over E. So that means E is going to be M L cubed over T squared. So we substitute. They say the data is in SI units, so there is no need of converting. M 0.2068, L 0.892, but it is cubed, divided by T 0.45, but it is squared. And oh, there was a K somewhere here. There was K somewhere there. So when I square, it is also squared, K squared into that. Then when I divide, K remains here. K remains there squared, so I'll multiply by K squared. And K is 1.48 times 10 power 5, but this is squared. So let's press the calculator. 1.48 exponent 5 squared times 0.892 squared times 0.2068 divided by 0.45 squared. So I am getting, you can also check your calculator. This is not conclusive. I am getting 1.7798 times 10 power 10. Because these are in SI units, that is kilogram per meter per second squared. That is the Young modulus in SI units. Then the uncertainty, I think, is now the easiest. So the uncertainty, we want absolute. They have given us percentages. So I will start with percentage. Percentage uncertainty in E is equal to the percentage in M plus 3 times the percentage in L plus 2 times the percentage in K plus 2 times the percentage in T. So we have 3 here because L is cubed. We have 2 here because K is squared. We have 2 here because T is also squared. So let's sum up the percentage uncertainties. For M is 0.1%. For L, so this is 0.1%. For L is 0.2 times 3 to become 0.6. So L is 0.6% plus. For K it is 1.5 times 2 it becomes 3% plus. For T it is 2% times 2 it becomes 4%. So when you add you have 7.7. So we want the absolute now. The absolute uncertainty in E is equal to 7.7 divided by 100 times the true value, which is 1.7798 times 10 power 10. So let's times 7.7 divided by 100. So I am getting this as 1.37 times 10 power, that is 36789. This is times 10 power 9. But then we said we also ensure that the uncertainty has the same power of 10 as the true value. So since the other one is to power 10, we also write this to power 10. So this will be, I move one step in that direction. When I move one step in that direction, then this is going to be 0.137 times 10 power 10. I hope the uncertainty is correct. I have to just cross check. K is 3. T is 2 times 2, which is 4. L is 0.2 times 3, which is 0.6. And M is 0.1. When you sum up, you get 7.7. Maybe I have to double check the true value of E, 0.2068 times 0.892 raised to power 3 times 1.48 exponent 5, and it is squared, divide by 0.45, and it is also squared. Oh, sorry, I'm getting a different value. I have to check it again to be very sure. 1.48 exponent 5 and squared. K is squared, then times 0.892 cubed times 0.2068 divided by 0.45 squared. Sorry about this. This is not true. This is not true. I have to change this. So this is actually 1.58. So 1.5876 times 10 power 10. So I have to check this also to change this. Of course, this does not affect the percentage uncertainty, so there is no need of checking it. So this would be times 1.5876 times 10 power 10. So I have to check that, times 7.7 divided by 100. So this is giving me 1.22. So I have to change this again. 1.22 times 10 power 3, 6, 7, 8, 9 power 9. Okay, so this is the same as 0.122 times 10 power 10. And then to one significant figure, of course I'm crossing out this will be approximately 0.1 times 10 power 10. This is one decimal place. So I'll write my value of E as 1.6. This one will be 1.6 plus or minus 0.1. Now I'll put all this in brackets, times 10 power 10. Okay, as simple as that. As simple as that. I hope my calculation is correct. You can always cross check. There is no problem with that. You can always cross check. Okay, next. The student measures the time t for one complete oscillation of a pendulum of length L. Her results are shown in the table. She uses the formula that to calculate the acceleration of free fall. What is the best estimate of the percentage uncertainty in G? So we make T this G the subject, square both sides, it becomes T squared is equal to 4 pi squared L over G. So G will be equal to 4 pi squared L over T squared. Then the percentage in G will therefore be ignoring the constant. So it will be percentage in L plus twice. This is percentage in L plus twice percentage in T. So we substitute, because we want percentage for L, we have 0.001 over 0.420 plus 2 times for T, that is 0.1 divided by 1.3. Remember, this is going to be times 100 because we are changing to percentage. Percentage in L is this over this times 100, this over that times 100. So we press the calculator, 0.001 divided by 0.420 plus, open brackets, 2 times 0.2 means 0.1 divided by 1.3, then times 100. So the answer is 16%. Oh, this is 15.6, 15.6, which is approximately 16%. So the correct answer there would be D. Next, without wasting any more time, calculate the density rho in kilogram per meters cubed. So they have given us mass, thickness, diameter. Density is mass over volume. So density is mass over volume. The mass has been given directly, but the volume has not. You know that volume is cross-sectional area times the thickness, h, where cross-sectional area is going to be pi r squared, this times h. But they have given us diameter, so we shall remove r, so it becomes pi d squared h over 4, because r is diameter divided by 2. When I square it, becomes d squared over 4. So therefore density will be equal to, when I substitute for the volume, the 4 goes up, becomes 4m divided by pi d squared h. You realize why I'm trying to come up with such an expression. It's because I know the uncertainties given are for the thickness, d and m. So if the next question tells me to calculate the uncertainty, I will not find any challenge if I've written such a formula. So substitution, this will be 4 times the mass, 9.6 times 10 power negative 3 to change it to kilograms. Divide by, this will be pi times d. D will be 22.1 times 10 power negative 3 to change it to meters, but is squared. The thickness is 2 times 10 power negative 3. Press the calculator now. That is 4 times 9.6 exponent negative 3. Divide by pi times 2 exponent negative 3 and 22.1 exponent 22.1 exponent negative 3 but squared. So I am getting, you can also cross check, you see what you get. So I'm getting 12513.15. So 12513.15. I'm not trying to reduce the number of decimal places or significant figures because I know I may need more when I'm writing a true value. So note that they have given us for the mass, uncertainty is plus or minus 0.5 grams. They have also given us for thickness as plus or minus 0.01. They have also given us for diameter as plus or minus 0.1. So we may need those values in the next part of the question. So normally I expect that B will be to calculate the uncertainty. So calculate the percentage uncertainty in density. Calculate the percentage uncertainty in density. We have already seen that, what has happened? I want a pen. We have already seen that the density is equal to 4m divided by pi d squared times the thickness h. So percentage in density, so we shall simply say percentage in density is equal to percentage in mass plus twice percentage in di, ignore 4 and pi, plus percentage in the thickness. Since they have given us absolute values, we just substitute. For mass, it was 0.5, so it's 0.5 divided by 9.6, of course, times 100 to make it percentage, plus 2 times for D, it was 0.1, divided by 22.1 times 100, make it percentage, plus for H, it was 0.01, 0.01 over 2.00 times 100 to make it as a percentage. Let's press the calculator very fast. 0.5 divided by 9.6. So this is 5.2. 5.208 plus the other one is 2 times 0.1 times 100 divided by 22.1. So this is 0.90. Then the other one is 0.01 times 100 divided by 2. So this is 0.5. So when you sum up, you get 6.6. So this is 6.6%. Then state the value of density with its actual uncertainty. So absolute uncertainty in density is going to be the percentage 6.6 divided by 100 times the true value of density. I think we got the true value of density on our previous page. Let's just go back slightly. This is 12513.15. Okay. So this will be times 12513.15. So let's just multiply 6.6 times 12513.15 divide by 100. So this is giving me 8. This is giving me 826 point 87. One significant figure, I think that is 800 and is ending in two zeros. So we are going to write this as a whole number ending in two zeros because this is 8, this is 800 plus or minus. So this will become 1300 to round off this so that it is a whole number. This will be 0, this will be 0. Sorry, no. This will be 0. Did I write the wrong value for that? 12513. Okay. So this is going to be 005. So this will be 500 plus or minus 800. So this will be the true value of the density with its absolute uncertainty. Okay, you can always cross-check. My pressing of the calculator may not be absolute, so you can always check. Next, an experiment is carried out to measure the resistance of a wire. The current in the wire is given as this. Potential difference is given as that. What is the resistance? Very first resistance is V over I. Of course, the true value, we take the true values, that is 8.0 divided by 1.0, that is 8.0 ohms, that is the true value. Then we check the uncertainty. So we shall say absolute uncertainty and resistance will be equal to absolute in V over V plus absolute in I over I, then we multiply by the true value of resistance. So this will be for V, that is 0.4 divided by 8.0 plus 0.2 divided by 1.0, and then this will be times 8. Pick a calculator. 0.4 divided by 8 plus 0.2, and this is over 1. Then answer multiplied by 8. So this is giving us 2. So this is giving you 2, which is a whole number. Therefore, our answer is going to be D. Okay, next. The Young modulus of a material is given by that equation. The wire is extended by a known force and the following measurements are made. Which measurement has the largest effect on the uncertainty in the value of the calculated Young modulus? The Young modulus is given by the equation below. The wire is extended by a known force and the following measurements are made. Which measurement has the largest effect on the uncertainty in the value of the calculated Young modulus? Okay, let's check. So the absolute uncertainty in A in the Young modulus, or the fraction in E, is going to be the fraction in F plus the fraction in L plus twice the fraction in D plus the fraction in X. So we can now check. In A, the length of the wire before force applied, L, is this. Let's check its fraction uncertainty. 0.02 divided by that. I think this is obviously small. Then we check D, 0.02 divided by 0.54. So D, then this is times 2. The fractional uncertainty here contributed by D is 0.707. Then we can check for F. I think this is 0.01, I guess. 0.01 divided by 19.62. It's already smaller than for D. We can check X. 0.2 divided by 5.2. It is 0.03. For X it is 0.03. So it's already D is the one which is contributing much. So the answer is B. It is the diameter which is contributing much to the absolute uncertainty. Okay. Next, the thermometer can be read to an accuracy of this. The thermometer is used to measure temperature raised from that to that. What is the percentage uncertainty in the measurement of the temperature raise? The percentage uncertainty. So let's find first of all the temperature raise. I think the temperature raise is 60. The raise equals to 60 degrees Celsius. That is the temperature raise. The thermometer can be read to an accuracy of this. Remember, in each measurement there will be that uncertainty. So the uncertainty in the temperature raise, I'll call delta T, is going to be twice this, because we don't subtract uncertainties. The uncertainty in 40 is plus or minus 0.5. The uncertainty in 100 is plus or minus 0.5. So the total absolute uncertainty is going to be twice 0.5, which is going to be equal to plus or minus 1.0 degrees Celsius. That is the absolute uncertainty in this rise in temperature. Then if I want the percentage, this will be 1.0 divided by the rise, which is 60, multiply this by 100. So this is 1 divided by 60 times 100. This is 1.66%, which is approximately 1.7%. So the percentage uncertainty in the measurement is 1.7%. Next, a digital caliper is used to measure that width of a plastic roller. The digital caliper reads to the nearest 0.01 millimeters. What is the correct way to record this reading? Okay, I think we have answered a similar question, but we can still answer it. First of all, we change this to meters. This to meters to be 28.50 divided by 1000. And when you divide that, I think this gives you 0.0285, maybe plus another 0. Okay, in meters. If that is true, or this is can be, because here we have power -2 and power -3, which can check. This is 1, 2. So it can be 2.85, maybe 0 times 10 power -2 in meters still. So it means this is not correct. It can't be 2.850 times 10 power -3. Okay. So you will notice that the correct answer is going to be C, because 1, this was changed to meters, but this was not changed to meters. It is still in millimeters, so this is wrong. Similarly, this is in meters, but this is wrongly converted to millimeters, because when you divide 0.01 divide by 1,000 to change it to millimeters, 0.01 divided by 1,000, you actually don't get this value here. You get 0.00001 in meters, which is the same as 0.001 times 10 power negative 2 in meters. So the answer will be C. Without wasting any time, let's go to the next question, 36. A microphone detects a musical note of frequency F. The microphone is connected to the cathode ray oscilloscope. The signal from the microphone is observed on the CR as illustrated. Okay, I think the question continues, but we shall use this same page. Let's just see the next question. The next question says the time-based setting is 0.5. Time-based setting is 0.50 milliseconds per centimeter. And then the Y sensitivity is 2.5 millivolts per centimeter. 1, they want us to determine the amplitude, and 2, they want us to determine the frequency. So we shall use the same page. We shall use the same page where we have our graph. Since we now know the X, the time-based setting, we know the Y sensitivity or the Y setting, we shall use the same page. So let's begin with the amplitude. The amplitude, so I'll just count this number of small squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then at the bottom we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 small squares representing the amplitude. But note that only 1, 2, 3, 4, 5 small squares represent 1 centimeter. So, but yet I have 11 small squares. So if one small square is going to be equal to 1 divided by 5, then 11 small squares will be actually 1 over 5 times 11. So that means 11 small squares are representing 11 over 5 in centimeters. I hope I counted well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is in centimeters. But note that the Y sensitivity is 2.5 millivolts per centimeter. Therefore, the amplitude is going to be 11 over 5 in centimeters times the Y setting, which is 2.5 millivolts per centimeter. So per centimeter is cancelled. So you have 11 times 2.5 divided by 5, which gives you 5.5. So this is 5.5 millivolts. Okay, so the microphone is connected to the cathode ray oscilloscope. The signal from the microphone is observed. Okay, so that's what we have. Then let's see the frequency. The frequency is equal to 1 over period. Period will be 1 over L times X. What is L? L is going to be the length representing one cycle, and X is going to be the time-based setting. So I'll start from here up to here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there are 19 small squares representing L. So, and remember, one small square is 1 over 5. So L is going to be a 1 over 5 times 19 small squares. In other words, it is 19 over 5. that is L, 19/5. Okay, so L is 19/5 in centimeters. And yet, the time-based setting is 0.5. Time-based setting is 0.5 milliseconds. So x is 0.5. Now I'm substituting. So frequency is going to be 1 over. So this will be 19/5 times, of course, this is in centimeters, times 0.5 milliseconds. That will be times 10⁻³ per centimeter is cancelled with the centimeters, so I just press the calculator. 5 on 19 divided by 5 times 0.5 exponent -3 exponent negative. So it means that L is 3.8 in centimeters. I will need that value. So 1 divided by the answer, 19 divided by 5 times 0.5 exponent -3. Okay, 1 divided by the answer. So I'm getting the frequency as 526.3 hertz. So that is the frequency that we are finding. We are not interested in waves. That was not my area of interest. So this is 5.5 millivolts. This is 526.3. That's not my area of interest. The actual uncertainty in F caused by the reading. So we are interested in the actual uncertainty F caused by the reading. The actual uncertainty F caused by the reading. So what is the actual uncertainty caused by this reading? So I will take you back to the graph. I will take you back to the graph straight away. I will take you back to the graph. So since one small square in the x, because we are finding the actual uncertainty in F. So since we have found F from L and the time-based setting is a constant, it is only L which is affecting the uncertainty. Therefore, the uncertainty in L is most likely going to be the uncertainty in F. So, the absolute uncertainty in L is going to be actually equivalent to the value of one small square, which will be 1 divided by 5. And this is going to be 0. This is going to be 0. I think that is 0.2. That is the absolute uncertainty in L. So since F is 1 over L times x, so I will ignore x, and therefore F is going to be 1 over L times x. That means the fractional uncertainty in F over F is going to be equal to, of course, this is like L power 0. This is like L power 0 divided by L times x power 1. So ignoring x, because this is the time-based setting has no uncertainty. So this is going to be like absolute uncertainty in L over L, because this will be power 0. Therefore, it means the absolute uncertainty in F is going to be 0.2, which is for L, divided by the value of L, which was 3.8 in centimeters. This is in centimeters. I wrote L here. So this will be the absolute uncertainty in L. And this will be equal to, by the way, this is going to be times F, times our value of F, because I take F the other side. And F is 526.3. So we are going to press our calculator, times 0.2 divided by 3.8. So this is giving me 27.7. So this is This is actually the absolute uncertainty in F. So it is 27.7. Then the next question tells us 27.7. The next question tells us to state F with its actual uncertainty. So just to remind you, on this page here, we have already seen that one small square is 1 over 5. So the absolute uncertainty in L on the x-axis was 1 over 5, which was 0.2 in centimeters. But then we measured L as 3.8 in centimeters. And we say that F was equal to 1 over L. X has a constant, is a constant. So this is L power 0, L times X. This is power 1. And this is the same as absolute in F over F is equal to 0, absolute in L over L plus 1, absolute in L over L. So remember, we multiply the powers by the fraction uncertainty. Of course, I ignore X because it's a constant. It is like a coefficient without an uncertainty. Therefore, we said absolute in F is going to be in L, which is 0.2, over L, which is 3.8, times now the value of frequency, which we got as 526, and this is giving me 27.7. So this is 27.7. So to one significant figure, this is approximately 30. This is approximately 30, so absolute in F is approximately 30. So I will write F as absolute is 30, ending with 1, 0. So this will be 530 as our value of F. Okay, let's continue next. A steel wire is stretched in an experiment to determine the Young modulus. What is the percentage uncertainty in Young modulus? So they have given us the load of the wire, they have given us the length, they have given us the diameter and the extension. So Young modulus is force over area times original length over extension, that is stress over strain. So we want percentage uncertainty in E. So percentage in E is going to be equal to percentage in F plus, they have area, no, percentage in L naught plus percentage in extension plus, now area, remember area is equal to pi d squared over 4. Pi, because it is division, it is in the denominator actually, so it is f over pi d squared over 4, and because it is division, we shall just add this times 2 percentage in D. So we just sum up. F is the load, that is 2%, so that is 2 plus L 0.2 plus E is 1 plus twice D, which is 3. So the percentage is, this is 6.2%. So our answer there will be D. Number 38. What is the correct reading on the thermometer and the uncertainty in this reading? So you see the divisions are fine enough, so we can approximate to half a division. The reading here is 20, 21, 22, 23, 24. So the reading is 24, but the uncertainty in a thermometer is plus or minus 0.5. And since it is half a division, because this is 1 degree, half a division is 0.5. It is 1 decimal place. So, and remember the uncertainty should have the same number of decimal places as the true value. So you have two choices to choose from, either this one or this one, but the most correct is this one because this is 1 decimal place. Yeah, this is just a whole number. So the answer will be D. Next. They have given us the resistance of a resistor is to be determined. The current I in the resistor and the potential difference V across it are measured. The results with their uncertainties are given as that and that. The values of I is calculated to be, R is calculated to be that. What is the uncertainty in this value? So from the formula, R is V over I. The absolute uncertainty in R is going to be equal to